Lesson 2. Drum roll, please. Lesson 2. This is called relations and functions. Functions. And I'm going to say it again because we're out here trying to function. You're out here trying to function. E40. 40 watt up. Do you remember this whole thing? So let's recall real quick. Let's recall the, I guess, fundamental problems we talked about last time. What were they? We only talked about 3 of them. There's 6 of them total. We talked about problem 0, and I hear Nas in my head. Money, 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 linear algebra is my money. Right? What's problem 0 from a student's perspective? How many of you all like that idea? That's why you're here, right? Because we promised that. It's a lie in college. We don't actually deliver that, but that's what we promise, right? All right. What would somebody that is more proper than I say? Using math, right? So that's problem 0. And in this class, what do we call math? Yeah, linear algebra. In other fields, you call math differently, right? But this is really focused on using linear algebra to model problems. All right, so that was problem 0. The hardest problem by far to solve. It is a difficult problem. That costs multi-million dollars. You have to have teams of engineers. That's why we don't do it in school. Because we don't have those resources, because usually states don't pay for that because we don't have lobbyists, right? That's called corruption. I'm going to say that right to my representatives. Get lobbyists out of my politics, please, right? So the other thing that I want to say was that when we're looking at problem 1, what's problem 1? Yeah, so this was the MVMP. Do you remember what that was? We said let A be an element of R. Yeah, I had a student yesterday, mango by November. That made me laugh really hard, mango. Because M and N sound too familiar, right? So we'll call it mango and November. Okay, so let A be an element of R, M by N. How many rows? Mango. How many columns? November. Be a given matrix. And in the matrix vector multiplication problem, what else do we have? Yeah. Let X be an element of R, N by 1 be a given vector. Why do I quote given? Yeah, because I should be hit in the face with a rotten tomato, right? Like, that's ridiculous. How can I say that you're just going to be given a matrix that helps you get paid? It'll never happen, right? But the assumption of mathematicians is, we don't have to worry about that. Just let it fall on our lap and let's analyze it, right? Engineers say, no, we have to construct those. That's part of our life, right? And I want to get you in that mindset that there's a construction phase and there's the analysis phase. Those are different phases of applied math modeling. What is the MVMP? Is to find an unknown and desired vector, right? It's like that great Mexican soap opera. That doesn't exist yet. Telemundo, make that one. Such that what is true? A times X equal B. Every single time. What does Haley Joel Osment sees dead people? What do we see? Matrix dimensions. I want you all to write matrix dimensions until you're blue in the face, and then I want you to do it 10,000 more times. Linear algebraists are slick as can be. You watch them in class, they don't write anything about dimensions, but in their mind, they've all calculated them. I want you to have the habit. Commit to making the habit. Every single time you write down a vector or a matrix, I want you to put little subscripts on that thing and check the dimensions until you literally can't help but see the dimensions before you write it. Then you can stop writing it. And for all of you, I'm going to set the bar high. That's at least 10,000 different matrices that you have to write dimensions on before you're allowed not to write them. Okay, how big is this one? M by 1. All right, what's the function under this? Under this problem, we had a function. We had a special function. When this function was born, its mother said, "You are very special," and that was true. Right? Called, what was the function called? Matrix vector multiplication function. All right, what was the matrix vector multiplication function? F of x equal a times x. This thing was predefined. This right here is called the input to that function, to the matrix vector multiplication function. Okay? So let's do some quick recall. What's the recall here? All right, I want you to sing a song to me. Anybody got the gumption to make yourself sound like a fool? Where did you come from? Where did you go? Where did you come from? Cotton Eye Joe. Right? What's that song all about? Yeah. Where do you come from? What do you put into the function? What type of information do you expect out of the function? What do you put into the function? What size vector is x? N. What do you get? What type of information do you expect out? M. And let's do a quick recall. Kind of like Total Recall, but not at all like that movie. So with the domain of f, what's the domain? Rn, and that's also equal to the domain space by less than 2, which is what we're about to get into. Okay, next one, codomain. What's the codomain of f? Rm. In general, this will not be equal to the range of f for most matrices. Well, the codomain of f equal to the range happens for special matrices. Very, very special matrices. Don't worry about this right now. I don't want you to, I'm not trying to trip you out right now. I'm just literally trying to, you saw that quote? What was the first quote in the syllabus? We never really understand math. We just get used to it. You know who said that? John von Neumann. He's one of the most famous mathematicians in the world. He helped design the first computer. He also helped create the atomic bomb, which I have some columns about. But I'm not trying to get you to understand this at a deep level. When we're constructing mathematics, I like to think about constructing a house. Each of you is going to construct your own concept images in your brain. When you do that, you're going to hang pictures on the wall, you're going to hang drywall, etc. But there needs to be a foundation. When we're setting these problems up, this sets the foundation for the entire class so that as we go through the class, you're going to hang stuff on this foundation. These 6 problems make up all of introductory applied linear algebra, at least in the way I see it. And so as we go through the class, the reason I'm having you do this now is so that you can start to set the foundation, and then you fill in the drywall, then you fill in the windows, and then you fill in the doors, and then you put your pictures up, right? And then you're like, damn, I never thought I was going to be a millionaire with a 100 square foot house. Silicon Valley joke right there, all right. All right, so these matrices are called full rank matrices, and we'll talk about that later. And really they're called full column rank matrices if you're going to be in this function. Okay, So in lesson 2, so let's just do a quick recall, and I'm not going to go over the whole thing. Do you remember what the problem 2 was?
Non-singular.
Non-singular linear systems problem. And then I just want the punchline of this thing. So what was I given in the non-singular linear systems problem? I was given a matrix, right? And what was different between this matrix and the matrix in the matrix vector multiplication problem? This one's square, the other one is rectangular, right? The other difference is instead of being given an input, what am I given instead? An output. And then what am I supposed to do in this problem? Yeah. It just so happens that for non-singular linear systems, there's a theorem that says this will always be in the range because the range is equal to the codomain. Right? That's a theorem. We're going to go through that theorem.
Oh, okay.
Yep.
What do you mean by singular?
Don't worry, we'll get there. I promise you I'm going to answer that question. Right now, I just want you to know that there's something called non-singular matrices. I want you to know there's something called full rank matrices. And in particular, what I want you to know is those verbs, or adjectives, I'm sorry, those adjectives relate to the relationship between the domain, the range, and the codomain. The differences between those in terms of solving these problems all have to do with how are the range and the codomain related. Okay, but in order to talk about that intelligently, could you guess what you need to understand? Yeah, so note the differences between problems. This is problems 1, 2a, 2b, and 3 all have to do with whether or not we should focus on the domain of f. That's one thing. What type of domain is it? What's the properties of that? And then 2, is the codomain of f equal to the range of f or not? So literally, to understand the most fundamental concepts in the first 4 problems, this is the matrix vector multiplication, non-singular linear systems, general linear systems, least squares. The entirety of all those problems, the most important concepts, come with where are we focusing? Are we focusing on given something in the domain, produce something in the codomain or the range? Are you given something in the range and then trying to find the pre-image? If you find the pre-image, how many pre-images are there? Is the thing that you're given in the codomain and not the range, in which case the problem is not solvable? Right? Okay, so I'm going to claim that in all the problems that we're going to focus on for the first 10 weeks of the class, these questions are going to be really important. Do you see an issue? Okay, I'm going to wake you up, go into your house, kick down your door, shake you awake at 3 a.m., and before you call the cops, I'm going to say, what's the codomain? Give me a mathematical definition of the codomain right now. Bet your life on it. You got it? Because it's not a prerequisite for the course. I'm ready to run now. Right? So, can you guess what lesson 2 is all about? Lesson 2 gives us the formal set theoretic language to talk about what is a domain, what's a codomain, what's a range, when are they different, when are they the same, what's a function, what's a relation, and do it from a mathematically rigorous standpoint so that we can abstract and talk about this in the context of linear algebra. So that when we get to those problems, you can discuss very, very cogently using that language what's going on with that. It should be a prerequisite, but it's not. All right, ready? Let's do it.